we now turn to the Neumann problem. The strong formulation was on this form, as we remember, and the normal vector on the boundary was pointing in this direction. Omega is here, and without saying anything about the boundary conditions, we got this general weak formulation. For the Dirichlet problem, we only used test functions phi, which had the property that the function was 0 on the boundary. Therefore, this term vanished, this boundary integral. For the Neumann problem, we have that the normal derivative of u is equal to 0. The normal derivative is in fact equal to the gradient of u multiplied with the normal unit vector on this boundary. So therefore, in this case of the Neumann problem, we can also say that this integral is 0. But the reason is different, because we identify gradient of u multiplied with n in this integrand, and saying that this should be equal to 0 on the boundary means that this integrand is 0 on the boundary. So therefore this integral must vanish also in the case of the Neumann problem. So we get exactly the same formulation of the Neumann problem as for the Dirichlet problem, with the only difference that these test functions phi should not any longer be members of the subless space W0. It should be members of the whole space W1, 2. And the solution u should also be such function. So we cannot say any more that the function u should have 0 boundary conditions, because for the Neumann problem this is not the case. So as before, we have this bilinear form a of u phi defined by this integral, linear form defined by this integral, and if we now assume that f is a member of the Lebesgue space L2, and that the integral of f is equal to 0, this means in some sense that we the heat source is the net heat source is 0, which from a physical point of view is a very necessary condition, because when we have insulated the boundary here, which is the Neumann condition, then it's impossible for us to have a net heat source in the system, because then the heat would build up and the temperature must go to infinity. So this is not, from a physical point, it is not a strange condition. Using these conditions, these two, we can prove that this will give this formulation of the Neumann problem will give a unique solution within an arbitrary constant. And what does that mean? Well, it does mean that if we have two solutions of this problem, u1 and u2, then the difference between these two solutions must be a constant in the area omega, the region omega. There are no we are now turning to some other examples of partial differential equations of the same type as the Poisson equation. Same type in the sense that they are called elliptic equations. At least this equation is an elliptic equation. It is the Poisson equation, and it can model temperature problem, but it can also model electrostatic potential. So where U is not any longer the temperature, but it is the potential. We have another example, convection diffusion problems. In such problems, we have some convection term. For example, if you consider heat distribution in between sheets, for example, where it's some air inside or a liquid or something, then we will have some transportation of the medium, which make it necessary to add some term here. So this is convection diffusion equation. Other type of equation, Stokes low speed flow equation, takes this form. We have biharmonic equation, which is equation modeling, for example, plate problems in 2D. So there are many types of equations in physics which we want to analyze, and all these type of equations can be described in such a way. The bilinear form is then different, and the linear form here is also different. And we will now show you some general rules for this. So generally we have some Hilbert space. This is usually a sublevel space, this capital V, and the norm in this Hilbert space is defined in the usual way. When we have a Hilbert space, we have also an inner product, so this will always be defined. Moreover, this bilinear form, which usually is some integral expression, is a bilinear form, which means that it's linear in both these two variables. And this is just a linear form, or a linear functional, which it is called when it's only dependent on one variable. So here we just remind you what linearity means. So we should also consider some examples of bilinear form. One example is bilinear form when it's symmetric. That means that A of uv is equal to A of vu for all values of u and v in this Hilbert space. So that's conditions which may be satisfied, and it may also not be satisfied. There are some examples of bilinear forms which are not symmetric. The other property of this bilinear form is that it should be continuous. And continuity is not so easy to describe for a bilinear form, but or visualize in the same sense as we know in the real case where we have only one real variable, but the definition is then more mathematical. And the definition is written as follows. The absolute value of this bilinear form should be less or equal to some positive constant C1 multiplied with the norm of U and the norm of V. So that's the definition of continuity of the bilinear form. Moreover, we have some other complicated property. A of UV should be V elliptic. Recall that V is just the symbol for our Hilbert space. So this should be V elliptic, means that there exists a constant C2 larger than 0, such that the bilinear form of any element in this, it is a function of course in this Hilbert space, and the same function should be larger than the constant C2 and the square of the norm of phi of the variable. So that's a complicated concept, but don't worry, we will give you some examples later on, and so you get some training in dealing with it. The fourth property is related to the linear form L. It should also be continuous. And continuity for a linear form means that there exists some constant C3 larger than 0, such that the absolute value of L of phi is less than this constant C3 multiplied by the norm of this variable. And this should be the case for any value of phi. So these constants, when I am mentioning that they are constants, it means that these inequalities takes place for any value. We don't need to change the constant for each for different values of phi in the Hilbert space.